So yesterday we introduced alkanes, alkenes, and alkynes. Today we're going to introduce functional groups. We're going to introduce structures that have heteroatoms associated with them, things like oxygen and nitrogen incorporated into the molecule. An example of a functional group that we're going to talk about today are esters. Esters are very common in the perfume industry. They're also very common in the flavor industry, because esters are found in a lot of the aromas that we get from fruit or things like pears, apples, bananas, honey, pineapple, for example. That aroma is coming from an ester. And so we'll introduce some of those structures today as well. Important announcements, Chapter 12. Chapter 17 homework is due on Sunday, August 2nd. We are entering the final home stretch of this course, so please let me know if you need help with any of the material or if you need extra time in any of the material. We're going to get to organic chemistry. We're going to finish Chapter 22 on Monday, and then we're going to do a brief introduction, modern materials, a little polymer chemistry on Tuesday. Wednesday will be a review. During our normal class time, I'll review for the final exam, and then the final exam is Thursday, August 6th, and then the chemistry in the news assignment that is due August 7th. Please email that to me as a Microsoft Word or PDF file, and please have the file saved as your name, your first and your last name, just so to help me keep those files organized so I'm not having to go through and reorganize and determine who I do have and who I don't have that assignment from. So a little review from yesterday's lecture, Nomenclature of Alkenes. We introduced alkane and alkene and alkyne nomenclature. So a little bit of a review. How would you name this alkene? What would you name this alkene as? Well, the first thing we want to do is we want to determine the length of the longest carbon chain, right? Number one, what's the longest carbon chain? And then after we find that, we want to count the chain in a way that gets the double bond to have the lowest number possible. So we want to count from the side. That gives the carbon double bond the lowest number possible. So we'll do 1 and 2 right now, longest carbon chain. So if I take a look, my longest carbon chain is pretty easy to tell in this case. I don't have any branches off of this carbon chain, but my longest carbon chain is this sequence of carbons right here. And then I'll count this carbon chain from the left, because that way I'll reach the carbon double bond with the lowest number possible. So carbon 1, 2, 3, 4, 5, 6, and 7. So longest carbon chain is 7 carbons, so that is hept. We have a double bond, right? So we're going to have ene in there at some point. Step 3, we want to name any branches, right, off of this carbon chain. And there aren't any, right? There are none. So if we can put that all together, right? Well, we have a 7-carbon alkene, so that's hept. The double bond is on the 3rd carbon, so 3-ene. We can add a little bit more to that name because we know the arrangement around that carbon-carbon double bond. If we look at that carbon-carbon double bond, both of the hydrogens are on the same side of that carbon-carbon double bond, and both of the carbon branches are on the same side of that carbon-carbon double bond. So that is a cis relationship. So we can add to the name and say we have cis hept 3-ene. I have a 7-carbon hydrocarbon that has a double bond at the 3rd carbon, and my arrangement around that double bond is a cis relationship. Those hydrocarbon branches are on the same side of that carbon-carbon double bond. So yesterday we introduced, like I said, alkanes, alkenes, and alkynes, functional groups that basically had just carbon-hydrogen bonds or carbon-carbon double bonds or carbon-carbon triple bonds. Today we're going to look at derivatives of that. We're going to look at the introduction of heteroatoms, functional groups that have nitrogen or oxygen, oxygen-carbon double bonds, oxygen-carbon single bonds in them, and then look at the variety of different structures that are possible when we start to introduce different atoms. And those are functional groups. They introduce different modes of reactivity, different properties to these molecules with the introduction of these functional groups. So here are some examples. We've already talked about the first two, alkenes and alkynes, double bonds and triple bonds. Today we're going to talk about alcohols, ethers. We're going to talk about amines. We're going to talk about aldehydes, ketones, carboxylic acids, esters, and amides. So as you can see, there's a wide variety of structures that are possible, a wide variety of functional groups simply by the introduction of one more atom, oxygen, and then another case, introducing nitrogen as well, in the case of amines and amides. So the first functional group that we're going to look at are alcohols. Alcohols contain a hydroxyl group. Essentially, what we're looking for is ROH, where R equals any carbon chain. So R can represent any carbon chain. And so taking a look at what this means, right? If I had the following functional group, hydroxyl group, which represents an alcohol, and I add that onto a structure. So if I had a 2-carbon alkane, it would be called ethane. If I had a 2-carbon alkene, right, it would be called ethene. And if I had a 2-carbon alkyne, it would be called ethyne. So simply by adding that hydroxyl group, I know that the hydroxyl group is there because you've replaced the ending. You drop the E and add OL. Drop the E and add OL to let us know that we have an alcohol present. So ethane becomes ethanol. Ethene becomes ethenol, meaning that you've got a 2-carbon, right? Ethene represents 2-carbon alkene. The OL tells you that you have a hydroxyl group present. And so we can see that in the name that helps us know what that structure represents. So a lot of organic chemistry is actually like learning a new language. You need to learn what are these different functional groups, what are they called, how to identify them, and how do I name them, so that when we're talking about these structures, when I tell you the name of a structure, the image of that structure pops into your head, or the key functional group of that structure pops into your head. So in general, alcohols are named by taking the name of the parent hydrocarbon dropping the terminal E and adding OL in its place. And we can see that even over here in larger alcohols, things like cholesterol end in an OL. If you've ever heard of retinol, that OL ending for retinol, just like the OL ending for cholesterol, is telling you there's a hydroxyl group present, there's an alcohol present in that molecule. So here's a question for you. Name the following alcohol. Well, our first step in this process should be to find the longest carbon chain that contains the alcohol. So my longest carbon chain that contains the alcohol is right there. I want to count that chain in a way that brings me the lowest number possible for the alcohol. So if I count this chain from right here, from the top, 1, 2, right? The alcohol is right there off of that carbon. So to have the alcohol with the lowest number possible, I'd start it right there. So 1, 2, 3, 4, 5, 6, and 7. So I have a 7-carbon chain. Any branches off this chain, I have a branch on the 2nd carbon. So on the 2nd carbon, I have a methyl group. So to put that all together, I have a 7-carbon chain, which would be heptane. And on the 1st carbon of that chain, I have an alcohol functional group. Remember, our branches off the chain are prefixes to the name. So to finish this name off, I would say I have 2-methyl heptane 1-all. I have a 7-carbon hydrocarbon that has a hydroxyl group on the 1st carbon, and I have a methyl group as a branch off of the 2nd carbon. So that's how I would name this alcohol. Ethers are the next example. They're a derivative of an alcohol where you've basically combined 2 alcohols together and you've lost water during the course of that reaction. So just like the alcohol was ROH, ethers are ROR prime. Again, where R and R prime can represent any carbon chain. Could be 1 carbon long, could be 110 carbons long. R and R prime could represent any carbon chain. They could be identical as well, for that matter. R and R prime could be identical carbon length. They could be different carbon length. It does not matter. An ether is a structure that has an oxygen in the middle of 2 carbon chains, a carbon to the left and a carbon chain to the right. R and R prime could be identical, or they could be different. And we name these by naming the longest carbon chain first, right? So that's the base name, the longest carbon chain. So the longest carbon chain I have here is 3 carbons. So 3 carbons is propane. And then the prefix is the remaining alkyl group. And once you add an oxygen, it goes from ethane or methane or propane to you add an oxy as the ending. So my 2nd carbon group, my shorter carbon group, contains the oxygen. That's just 1 carbon, so that would be a methyl group, but because you've added the oxygen to it, it becomes methoxy, indicating you've got a hydroxyl group on the molecule. So now putting those 2 pieces together, right, the name of this ether would be methoxypropane. Ethers are really good solvents. They are non-reactive in the most part. And early ethers, like this example here, commonly known as diethyl ether, were actually used for a long time for anesthesia. So to name this diethyl ether, following IUPAC nomenclature, we want to find the longest carbon chain. Well, in this case, both carbon chains contain 2 carbons. So it doesn't matter which one we pick as the longest and which one we pick as the shortest. So I'll just say, here's my longest carbon chain. So that would be the base name, right? 2 carbons is ethane. And my shorter carbon chain that contains the oxygen, right? My other carbon chain would be ethane, but because it contains the oxygen, it would become ethoxyethane. And that's how I would name diethyl ether. That would be the IUPAC name for diethyl ether. The next category of functional groups are carbonyl functional groups. And so carbonyl is kind of a broad umbrella, And under that umbrella, we're actually going to find 5 different functional groups. And so a carbonyl is kind of classified as, we have this carbon-oxygen double bond. That is a carbonyl. But within that category, we'll have amides, aldehydes, carboxylic acids, esters, and ketones, depending on what X and Y are. X and Y can change, and so if X and Y are both carbons, we would have ourselves a ketone. If X is a carbon but Y is an oxygen, we could have a carboxylic acid, we could have an ester, or if X is a carbon and Y is an amine, we could have an amide. So there's a couple different functional groups that fit under this heading. And so the functional group is not known as a carbonyl. Rather, carbonyl is this carbon-oxygen double bond, and that is found within all of these different functional groups that we're going to talk about. Aldehydes being the first functional group that we're going to talk about that are within the carbonyl family. Aldehydes are characterized by that carbon-oxygen double bond, and that carbon is attached to at least one hydrogen. As you'll see for these aldehydes, we have 2 different names present. We have the IUPAC name and the common name. So many of these smaller molecules will have 2 names, both the IUPAC name and a common name that we also know that structure as. But again, to see where that name comes from, the first example is a 1-carbon aldehyde. 1 carbon, that'd be known as methane. The aldehyde is indicated by an Al ending, so we drop the E from methane and we add Al. So the name goes from methane to methanal. Again, that Al telling us that we have an aldehyde present. The same would apply to this 2-carbon aldehyde. 2 carbons is known as ethane. We're going to drop that E ending and we're going to add an Al, and this will become ethanal. Again, that Al indicating that you have an aldehyde present in the molecule. And so here's an example, right? Any aldehyde, we're looking for this general feature, RCHO, where R is any carbon chain. And we're going to look for that ending, that Al ending, indicating that we have an aldehyde present. So how would you name this following aldehyde? Well, I would look at the aldehyde and I would count the carbons present. In this case, because aldehydes have to be on a terminal carbon, we do not need to number where that aldehyde is, but you still need to know how long that carbon chain is. So I have a 5-carbon chain. So 5-carbon chain, that would be pentane. I'm going to drop that E ending, and I have to add Al to that to indicate I have an aldehyde present. So putting that back together, the name for this would be pentanal. A 5-carbon chain that has an aldehyde present. Aldehydes are very common in aromatic compounds that you have maybe experienced in the flavor industry or the aroma perfume industry. So benzaldehyde, it's actually the oil of almonds, so it smells very faintly of almonds. I've actually worked with vanillin and cinnamon aldehyde both. So vanillin is the extract of vanilla. And sure, there are certainly other functional group present, but aldehyde is a key functional group in these structures, and the same with cinnamaldehyde. I actually used that for a couple different reactions in grad school, and gives the lab a very subtle aroma of cinnamon. So whether you knew it or not, you've probably come across a few different aldehydes just in baking and working with different things. A lot of those aroma compounds can be related to either aldehydes or, as we'll see in a little bit, esters.